Hi, everybody. I first want to say thank you to Cardo for the invitation to come and give a talk. My name is Mark Korver. I'm based in Seattle, which as far as I know is still considered Amazon's #1 headquarters. I'm going to give a little talk today, kind of going back into the history of what we're now calling Cloud-native Geospatial, and then how that hopefully will inform us as we go forward in this world of GenAI and large learning models, et cetera. So before I start, just a little bit of my cloudy background. You can probably tell I've been in this industry for more than just 10 years. But I have over 10 years, over a decade. I think it's going to be closer to probably 11 as an AWS solution architect. So you can think of me as, back when I joined AWS, there was like 30 people on the public sector side of Amazon Web Services. I was one of the first solution architects to get hired. I founded and I lead what we call our AWS Geospatial TFC. TFC stands for Technical Field Community. So you can essentially think of that as the group at AWS that has solution architects. Most of us have some variety of backgrounds in geospatial, everything from folks involved in national security analytics to people who understand how to split parcels at a county level kind of thing, and everything in between. And so when we have account teams come to us with customers with geospatial use cases, we're called upon to help them as specialists in geospatial, help them along in their use cases. I'm also an honorary member of our AWS Open Data team, and I'll talk about that a little bit more. But I bear some of the responsibility for why we've put a lot of effort into a variety of open data, but more specifically geospatial open data. And then more recently, from 2022, I'm the BDM, Business Development Manager, for geospatial on our aerospace and satellite global solutions team. So yes, as I say here, cloud in space. So today, I wanted to talk a little bit about what, at least in my mind, I think of the paradigm flip. So if you asked me, what's the most important thing that happened to geospatial because of the cloud, then I would say it's probably this idea of flipping the data paradigm. And what I mean by that is moving from data to code to data, or downloading data to uploading code, right, to data. And I want to talk about that a little. So a little bit of the history of how that actually happened in the cloud. It took a long time. So AWS, it's been around for a while. We started, technically in 2004, more generally in 2006. But we're talking over a decade of this kind of work that got us to where we are right now. So I'll speak to that a little bit. And the primary point I want to make is it was a combination of open source efforts around open source, enabled by the cloud, that made all of this happen. So just so I can kind of define my terms a little bit, right? So before was the world of downloading data. And, it's simple. It's in order to work with geospatial data, and then I should caveat this a little bit. I'm generally talking about raster data, imagery data, right? Nowadays, it might be SAR data or LiDAR data. But in early days, it was mostly imagery data, right? And so, what that meant was that we'd have to copy data. We'd have to copy data to local storage, assuming you had enough of it left on your server, your notebook, or your file system that you had local, right? And then you work on that data after you downloaded it. And all of us remember, right? It was always hard to delete data because the effort of downloading data in itself was a pain, right? And so deleting data was a hard button to push. So, and another way I think about it, especially for those of us in the Earth observation world, was having to deal with FTP servers, right? Waiting in line, FTP servers, literally getting email from FTP server admins who weren't happy about how you were, putting pressure on their system, I guess you could say. So, and then, what's really important here is that there would, typically be, some kind of authoritative copy of the data available on FTP server. And the world of us, right, doing some kind of spatial data science, were happily downloading it and spreading it all over the place, right? So a zillion copies of the same thing all over the place, typically with, iffy metadata, right? What happened to it? Where did it come from? When did I do this? And so I'm laughing about this, but you remember when, for those of us who are into music, MP3 files before Spotify kind of thing, right? And a really big part of this that we don't probably talk to enough is that any kind of update, like if the scene changed or there's a problem with the data, that would get reflected a zillion times, right? Most of the time people didn't know, right? And it was hard to change things after the fact, especially after been widely distributed. So I'm moving away from geospatial and talking more generally around big data analytics. So when we first start seeing the term moving code to data, could very well have been in the Hadoop in Action publication back in 2010. I'm sure people were talking about this before that, but in terms of something you could buy on Amazon.com as a book, right? It's like 2010. Right? You see this term being used. So what does this mean? So for those of you who don't know what Hadoop is kind of born out of Google's file system paper that was published way back in 2003 already. And the reason Google's publishing something like that is because Google at Google scale already back in 2003 had a huge storage problem, right? They couldn't just put all the Google data on one server and call it a day. They had to have a lot of servers and they had to spread that data out, right? So that's Google File System, the GFS. And then Hadoop, essentially was able to use the Google File System or something like it, right? To spread data out across many servers, across many hard drives, and essentially run code against that distributed data in a highly parallel process. And the Hadoop project, Hadoop became an Apache project way back in 2006. So this is kind of the birthplace of this kind of general idea of distributing data on a not on a traditional file system, and then running code, chunking the data and running and chunking the application or the jobs against that data against the file system or the distributed file system. So here's a picture I stole from the web that gets us across, right? But note here that the data is distributed. There's just 4 machines here. And then the algorithms go. So you have a mixed, code and data type scenario here. So this is the early days of code to data. And then in 2009, AWS, we announced something called Amazon Elastic Map Reduce, EMR. And basically what that is a managed Hadoop infrastructure. So we make it easier for you to do big data analytics because you don't have to worry about the details of running a Hadoop cluster kind of thing. That was in 2009. And if you think about, so the early days of EMR managed Hadoop on AWS, right? It was really, pretty much the same thing, just that you're running it on virtual machines, EC2 in our case, and we were doing the heavy lifting for you. But it was right next to, some of our initial and long-running services by that time, right? Things like Amazon S3, our object store. And it took a while for the kind of the ecosystem of customers that are using Amazon EMR to start using object store within that context. It didn't happen immediately. And kind of the timeline on this is, we started with Hadoop, managed Hadoop EMR in 2009, but it wasn't until 2014 that we announced something called EMR file system, which is essentially using Amazon DynamoDB, another service, to sit on top of object store Amazon S3 to provide consistency to that data. So you can read and write data in a consistent fashion, right? It took some time. And the point I'm just trying to get across is for the kind of the storage side of those Hadoop environments to become more cloud native, it was years of work, years of effort, and it is kind of a cultural thing too, right? And then in 2020, we're getting much closer to current times. S3 announced consistent read and writes, so you don't actually need EMRFS anymore. And I'm not going to talk about this last one today, but if there is one of these kind of data points that I'd like to take home is the object store providing consistent read and writes. And for those of you who don't know what I mean, it means that you could write something to the object store or delete something to the object store. And the next time some application, either your application or somebody else's application, either did a get, a read, or on that same data, or went to look for the data, it would be consistent across not just your application, but any applications. This is a huge change for S3. This is kind of quietly announced, but I suspect that this one little data point will change the world. And you can see that in projects now, for example, Apache Iceberg, for example, is an example. So the general idea of treating the object store not just as a place to stash data or stage data, but as a database, right, that scales globally. So this is a big item. Here's a picture, kind of similar to the one I showed earlier. This is kind of the best I can do with graphics, so I apologize, there's no interactivity here. But the code is on the left, and there's some kind of scalable compute in the middle, and there's an object store on the right, right? Now we have truly decoupled compute from storage, right? So in the middle there, if you come to AWS now, we have over 200 services. My job is to help you navigate, what options work best for your use case. But the scalable compute cluster in the middle could be everything from the original EC2 auto scaling, right? Where nowadays you may choose to run or not run Docker, or it could be, Fargate that looks a lot more serverless, right? You don't have to worry about the details of how many EC2 instances or compute nodes you're running. Or it could be, for example, API Gateway Lambda, which we call one of our serverless. It doesn't really matter. It's compute in the cloud, right? But it can interoperate with object store. And I just want to point out that I'm looking for the person that's telling me what time I have left. Okay, got it, okay. So I just want to point out that the object store is greatly simplified, right? Remember Google File System. There's many servers involved. The data is spread out, right? But from the application perspective, it's just an HTTP get or put, right? It's vastly simplified. You don't have to worry about the complexity of that. So going back a little bit, the genesis of AWS, 2004 was SQS, our queue service, right? 2006 was S3 and EC2, and then 2007, Simple DB. I became a customer in 2008 before I joined AWS. This is all there was, right? To get started on EC2 was, scratching my head for like a morning to get virtual machines up. Now there's many more things, and we're happy to help you with that stuff. But the point I want to get across is, look how much serverless it is, right? There's virtual machines, EC2, But it wasn't really until recently we started talking more about serverless architectures. But if you look at the start, right, and especially if you look at things like SQS, running jobs via SQS, batch processing via SQS, and how we store data, the beginning was very much serverless. And this is important, right? This is, I'm assuming here and I'm probably not being clear enough about this, but this general idea of cloud-native, geospatial overlaps with not having to do things like manage servers. It's serverless. They're RESTful endpoints, all of these things. Right? And so in the beginning, the early storage options were ephemeral instant store on EC2. What that means is that as soon as you turn off the virtual machine, poof, you lose your data, right? Amazon S3, the object store, SQS, and SimpleDB. So we didn't have elastic block storage. We didn't have EFS. We didn't have SFS, a long list of storage services that we have nowadays, right? And essentially what that meant is that as developers or solution architects you had to build, you're forced to build stateless applications. There's a forcing function, right? Now you don't. You can build stateful things a lot easier. And so the general idea I want to get across here is that the earliest days of the cloud actually force you to build in a more cloudy way, right, so to speak. And then I'm finally getting to the geospatial part here. So it was in 2006 that there's a discussion, and the one I found was Chris Holmes' WordPress back 2006, where Chris is actually referencing or referring to a post by Chris Tweedy back then, talking about using Amazon S3 as a way to, as a place to cache tiles, right? And in the context of this is essentially along the lines of, I'm running, for example, OGC WMS requests. I'm generating some kind of image, and I want to take that and then tile it. And tiling here is specific to OSGeo tile map service, which came about because Google did Slippy Maps or came out with Google Maps back in 2005. So obviously there's going to be an open source initiative to do Slippy Maps. Outside of the control of Google Maps, right? And that was OSGeo tile mapping service. So the first kind of discussion around how to use things like Amazon S3, object store for specifically geospatial purposes had to do with caching tiles, map tiles, 256 by 256 map tiles that we use like every day nowadays, right, on our phones, et cetera, right? So it's the norm. That happened at scale thanks to Google Maps back in 2005. In 2006, open source community was trying to figure this kind of stuff, of course already, but more specifically in the cloud. So here it is, so OSGeo tile map specification. I was looking at this, and last got edited like in 2012, but it predates that. There's, of course, a nice, if you want to go and learn about this, the MapTiler folks have had a really nice demo out there for years now, where you can understand how this kind of quad tree-like mechanism for tiling works. That's what they were talking about, right? Putting this in the cloud. So now I'm jumping to, the tiles are a byproduct of some kind of geospatial query, right? And the source data, if you're talking imagery, is going to probably be a geotiff on object store. So initially, most folks were running on virtual machines in the cloud, and they're using ephemeral store, as I mentioned earlier, or EBS, to load that data. What did that mean? It meant copying data from Amazon S3 to EBS, right? The same copying, but in the background of these servers. It didn't work. It didn't work at scale because it took a lot of time to copy large imagery files. I know I'm probably getting close to time. So back in 2014, I gave a presentation at the FOSS4G conference where I'm talking about using Fuse to mount Amazon S3 buckets such that GDAL or GUDAL could read it, right? This is the beginning of not using EBS to store thousands, hundreds of thousands of GeoTIFF files. There's a 2014 post here by Frank Warmerdam, who founded GDAL, pointing at my video talking about how this works. But more interestingly, he was at Planet doing similar things. And he mentions in this post where he's using VisiCurl to work with data in Amazon S3. So this is Planet back then. Frank helped us getting Landsat 8 data available in the cloud. This is before the USGS was doing it. This is us working with folks like Planet and others to make data such as Landsat 8 generally available. Before Landsat 8 was actually USDA NAEP, which I did myself. And then in 2016, there's this big announcement from Digital Globe. Obviously, folks like Digital Globe, now Maxar, are looking at the work that others were doing in open source world, such as Planet, et cetera, and they're moving a whole bunch of stuff that was on tape into the cloud to S3 and Glacier. And then in 2016, we announced the Earth on AWS program. So this is our first kind of specific foray into not just open data, but Earth-specific data. And in that blog post, we mentioned, of course, the Landsat thing, which happened, was made available in 2015. But already by then, there had been years of effort around making these kinds of data sets available in the cloud. Right? Here's the Earth on AWS page. I want to put this up here because we're hoping to soon add visualization to it, which will make the data available to more lay people that don't know what a GeoTIFF is. They can actually see the data because there's many petabytes of data in the cloud already. If you haven't seen this already, please go look at the Registry of Open Data. This is where you can find all kinds of data, not just geospatial data. Here you see Sentinel data listed. And of course, this is about GenAI, so I talked a little bit about, I had to ask ChatGPT about object store for geospatial. And it gave me quite a good list, right? It was pretty impressive. But I won't go into detail here, but the one thing that kind of caught my eye was how integration with geospatial tools at the bottom was at the bottom. And I'm assuming there's some kind of priority going on here with ChatGPT. I didn't like that. I don't think it actually made sense. And the reason is, GDAL support for Amazon S3, specifically for geospatial data, is a good part of the reason why object store became the solution going forward. So you see this happening. So basically, S3 being supported by the GDAL project way back in 2015. GDAL support for cloud-optimized GeoTIFF, 2016. And then in 17, this is a huge win for many of us, was being able to deploy virtual machines in the cloud and not have to worry about keys and security, right? So GDAL can read directly from your secure object storage. So for the commercial data providers, this was a huge item here. That's back in 2017 already. So GDAL added capability that made both the technical and economic value of object store much, much greater. It was a combination of those two. Okay. So I'm out of time, so I'm going to stop here. I had some more slides, but please, I'll be around the rest of the day. Hit me up. Happy to answer questions. So thank you very much.